Okay, so now it's actually time for us to do math. I know, you were thinking, I finally escaped math. I'm going to be an engineer. They're like artists, right? Okay, you didn't think that. You've been doing math for a long time now. But you're a silly professor who has to make stupid jokes because I'm a dad and I'm required to by law. So what we have here is we have two gears. They're connected by the teeth. Motor turns gear A with a constant, I like that word, angular acceleration of 4.5 radians per second squared, starting from rest. Now the cord is wrapped around pulley D, which is rigidly attached to gear B. Ooh. Okay, so what are you trying to find? Well, the velocity of that cylinder and the distance it travels in 3 seconds. So you're taking angular acceleration. You're going to figure out how much this changes by comparison, and you're going to figure out how this cord is being moved by this rotating body. There is a lot going on here, and you haven't used these equations before, but because I'm deciding to be mean, I'm going to throw you off to do this on your own, and then you'll come back and you'll look at it and see, oh, well, that's how it's done. But go and struggle a bit, try and see if you can manage to figure it out. And if you can't, that's okay. Now, as a note, if you've taken my solid mechanics class, you're probably going to have an easier time of this just because we've already talked about gears a lot more. Spoiler alert, and a little plug there for solid mechanics. Okay, so go forth, try it out, and then we'll come back and rock it together. And oh, I'll give you a plan. There you go. A plan to help yourself out. So 3, 2, 1. Okay, you tried the problem out. It went well, it went terribly. I don't know. I'm just a video. So let's try it out and see how it goes for us. First off, one thing we need to realize is that gear A and B will have the same speed and tangential component of acceleration where they mesh. What do I mean by that? Well, if I've got 2 points and they're connected, then for equilibrium, this point right here on either one has to have the same velocity and acceleration. If it doesn't, everything breaks. But what's our equation for velocity and acceleration? Well, we know tangential acceleration is equal to our angular acceleration times our radius. And so that would be the same case for gear B. Now, I don't know what the angular acceleration of B is, but since I know that they have to have the same angular acceleration, the same, tangential component of acceleration, then I know that these two are equal. So I plug in all my numbers. Here is the radius for both. Here's the angular acceleration I know. And I can solve and I see, okay, that's going to be 1.5 radians per second. As a note, it's actually related based on the ratio. That's going to be the case for a lot of different properties. So 225 over 75, that equals 3. That is the gear ratio. You see that a lot in different cases. Okay, continuing onwards. Now, gear B and pulley D turn together. If they turn together, they have the same angular acceleration because they're locked in step. I mean, pulley D, you could say it's just simply a point on gear. That is a terrible gear, but you could say it's just like a point on gear B. Now, this is also all constant. And then here we have some assumptions. Now, if anybody comes with you the whole, like, oh, you know what they say about assuming? For one, you should say, no, I don't, but you assume I do. And two, you're an engineer. You have to make assumptions. In this case, we're saying that that cord doesn't slip and that it doesn't stretch. That's what inextensible is simply saying there. So, what that means is the velocity and acceleration of the cylinder will be the same as the velocity and tangential component of acceleration for pulley D. Just the tangential component, though, for pulley D, because the normal component isn't doing anything for this. So therefore, the acceleration of C is equal to tangential acceleration at D, which is equal to the angular acceleration of D times the position vector. Okay, be very, very careful. It's so easy to get the angular acceleration and the tangential acceleration confused. Remember, one's in radians per second, that's talking about turning. The other one is in meters or feet per second squared, and that is going in a straight line. So we solve this and we see, okay, the acceleration of that cylinder C is going to be 0.1875 meters per second squared. And since our original angular acceleration is constant, acceleration B is going to be constant, which means the acceleration of D is going to be constant, which means the acceleration of C will be constant. Woo! So this will be a constant acceleration. So then we can use our nice, simple kinematics equations to solve for its velocity and position after 3 seconds. Because we know it starts from rest, we start from 0 here, and so all of these simplify really nicely. And that's it. That's the end of this problem. But the biggest thing here was not getting to these two equations. These equations are easy. It was realizing how all those gears connected. And I know that you're new to this. I know that's not necessarily easy. But if you practice, and I want you to try some problems on your own as well, hopefully it will begin to make more and more sense. So thank you all for listening. I hope this helps you. And I'll see you all next time. Okay? Have an absolutely wonderful day. Bye-bye.